So problem number one was a properties of exponents problem, and you honestly couldn't do this if you didn't know your properties of exponents. So um, to refresh your memories, there are more properties than these, but these are the main ones we typically use. First one here is the product property. When you multiply like bases, you can condense them together by adding the exponents. The quotient property, the division property, is the exact opposite. When you divide like bases, you subtract the exponents. The power property, if you have exponents on top of other exponents, you multiply them. And then the negative exponent property says if any base has a negative exponent, that negative tells you to reciprocate the base. Now there are lots and lots of different ways to simplify these expressions. I'm only going to show one way, the way I see it, but definitely this is not the only way to do these. The first thing I notice is I see a parentheses and an exponent on the outside, so that tells me to use the power property. I'm going to distribute the exponent of 4 in. Now anything I do not highlight, I'm simply going to copy down. I'm going to take things one step at a time so I do not confuse myself. So distributing the 4, that gives me x to the negative 4, y to the 16, z to the 8. The next thing I'm going to do is I'm going to clean up the numerator a bit. And again, notice how the numerator, everything's just multiplying each other. There's no timesing, or there's no adding and subtracting. So this is all the product property. Also note that these properties, they only work for like bases, which means you don't mix up the variables. So you only do x's with x's, y's with y's, z's with z's. In this case, there's only x's and z's that I need to do stuff with. The y in the numerator, at least, is just by himself. So again, anything I don't highlight, I'm going to just rewrite. So with the x's, x to the negative 2 times x to the positive 2, that gives me negative 2 plus 2 is 0, and I guess I should add one more to the list. Anything to the 0 power is a 1. So the x's, I don't have to bother writing because, 1, it vaporizes. Moving on to the y's, the y to the 4 is just by itself, and the z's, negative 1 plus 4, gives me a positive 3. And then everything in the denominator, just copy down. Next, here, I'm going to apply the quotient property, and again, you only look at the same variables. So I'm going to look at the y's, and I'm going to look at the z's, and oh heck, let's use the negative exponent rule for the x's. So using the negative exponent rule, the x will go on the top, and that becomes positive. Now for the y's, if you take a look at the quotient property, notice right here, it does say a minus b, and a came from the numerator. So technically you're supposed to do numerator minus denominator always. However, I like to do big minus small, and then simply put my answer wherever the bigger number is. So for the y's, I'm not going to do 4 minus 16, but instead I'm going to do 16 minus 4, which gives me 12. But I'm going to put the answer of y to the 12th in the denominator because that's where the bigger exponent was. Same thing with the z's. For the z's, I'm going to do 8 minus 3, which is 5, and I'm going to put my answer of z to the 5 in the denominator because that's where the bigger exponent was. So that is the simplified form. Number 2 is really the same thing, properties of exponents. The only thing that's different is fractions. And I hate to say it, we can't escape it. We can't forget about it. At this level, you have to be comfortable working with fractions. And if you're not comfortable, you have to know how to use a calculator to get you through it. So I'm sorry if number 2 was hard because of the fractions. You just got to find some way to get over it. But the properties themselves are 100% the same. So the first thing I notice is exponent outside of parentheses. That tells me to distribute. So I have x to the 5/12, y to the negative 1/6, and then just copy everything else that's not highlighted. Times x squared, y to the 1/4. Next, I'm going to clean up the denominator a bit using the product property. So I have x's here, I have y's here, and the z's are just by themselves on the bottom. So that's x to the 5/12, y to the negative 1/6, over x times x squared is x cubed, y to the 3/4 times y to the 1/4 is just y to the 1, and then z to the 7/4. Then last but not least, use the division property, the quotient property. So I got y is here, or x is here, and y is here. Again, technically you're supposed to do top minus bottom, but I'm going to do big minus small. So for the x's, I know 3 is bigger, so I'm going to do 3 minus 5 twelfths, which is 36 twelfths minus 5 twelfths, which is 31 twelfths. And since the bigger exponent was on the bottom, my answer of x to the 31 twelfths goes on the bottom. Move on to the y's. I have 1 minus a negative of 6, which is 7 6. And the bigger exponent was on the bottom, so put the 7 6 there. And then z was just by itself. Now I have nothing left over in top, but just can't leave it at 0, so there's always 1 left over. Technically, I do have some fractional exponents. Those are radicals, and we like things rationalized, but we did a lot of work here. I'm not going to make you rationalize. So that should be the answer, the simplified form of number 2. Number 3, talking about rationalizing. The idea of rationalizing, at least with radicals, is to get rid of it. Now the idea is to know the opposites. We should know that a square root and an exponent of 2 are opposites. A cube root, well, that's an ugly cube root. A cube root and an exponent of 3 are opposites. A fourth root and an exponent of 4 is opposites, so on and so forth. So in this particular instance, to simplify or to rationalize the denominator, the instruction did say denominator, I need to get rid of that square root in the bottom. Well, to do that, I need a square. Squaring means multiply by itself 2 times. So that's exactly what we're going to do. We're going to just multiply top and bottom by radical 10. So you just go ahead and multiply straight across, 3 times rad 40 over, and the whole point of multiplying a square root by itself is we should know a square root times itself, the radical goes away, that's just a regular 10. Now the instruction did say simplify, so we have to simplify that rad 40, and I hope everyone understands or knows that 40 is the same thing as 4 times 10, and that the square root of 4 is just 2. So this 2 squared to 10 is just that radical 40 there, and I still have that 3 on the outside, so that when I write down my next line, I need to keep that 3 there. Then I'm going to change the rad 40 into 2 rad 10s, and then I can multiply. Now when it comes to simplifying radical expressions, you have to look at the outside numbers separately from the inside numbers. So when I ask myself, hey, can I simplify this? I'm only looking at the 6 and the 10, which we know we can divide out of 2. So the final simplified form should be 3 rad 10 over 5. Number 4 is the same concept, except instead of a square root, we now have a fourth root. Well, we know that an exponent of 4 will cancel out the fourth root. So look at what we have here. We have a 5. We want to cancel out that fourth root of 5 to the 4th power, which is just 5 times 5 times 5 times 5. We already have one 5. We want 5 times 5 times 5 times 5. So I hope it's not, a big stretch of the imagination to know that we need 3 more 5s. Or in other words, we need a 5 cubed. So that's exactly what I'm going to multiply by. I'm going to multiply by the fourth root of 5 cubed. Of course, what you do on top or bottom, you got to do it on the top as well. So you go ahead and distribute that guy. So that's going to be 8 fourth root of 5 cubed. What's that? 125. 125 plus 125 times 25 is 3125 all over. And again, as before, the whole reason for doing this is that the fourth root cancels and we're just left with the regular 5. Now it's time to simplify those radicals. Well, the fourth root of 125, we know it doesn't simplify because we are the one who injected it. So I know that this one stays the same. We need to simplify the fourth root of 3125. Well, I know that 3125 is just 5 to the 4th times 5. And then the fourth root of 5 to the fourth is just 5. So that simplifies to 5 times fourth root of 5. Now, when it comes to simplifying fractions with radical pieces, again, as I said before, you have to look at the outside numbers, and you have to look at all of them. So I have to look at the 8, I have to look at this 5, and I have to look at this 5, and I have to ask myself, is there a single number that I can divide out from all of them at the same time? And the answer is no. So this is as simplified as possible. That is the rationalized form of number 4. Number 5, I'm rationalizing with a binomial. So I need to put a square on this guy, but he's on a binomial. Now the only way we can square individual terms in the binomial is to exploit this pattern, the difference of two perfect squares. Because we should know that a minus b times a plus b is a squared minus b squared. A common mistake I saw people trying to do is this, and they thought, oh, that's just going to distribute a squared minus b squared. That is false, because the pattern goes a squared minus 2ab plus b squared. So if you just try to square a binomial, you're going to have this extra middle term here, which does not simplify things. So we can't, or we should not use it. Instead, we should use this pattern. So the idea is to just multiply by the reciprocal of the denominator. Now, what about this negative here? He does nothing. Just carry it through the problem. So this equals a negative, and then just go ahead and distribute. 21 rad 2 plus 3 rad 10 over, now in the denominator you could FOIL them out, but you shouldn't have to, because we have this pattern here. We know it's going to be the first term squared, so 7 squared is 49, minus the second term squared. Radical 5 squared is just 5. So that's negative 21 rad 2 plus 3 rad 10. 49 minus 5 is 44. And again, you have to ask yourself, look at the outside numbers, the 21, the 3, the 44. Is there anything I can divide out from all of them? The answer is no. So that is as simplified as possible. 6, 7, 8, 9 are all factoring questions, and I hate to say this, but it's sort of things that you either know how to do or you don't know how to do. There is no formula, there is no algorithm, it's all logic, guess and check. So if you are not good at factoring by now, we need to practice some more. I do have some general tips, hints, and a process that I'd like to think through, and this is it. I know it's going to factorize into the product of two linear factors. Whatever I put in the first positions has to multiply to the first term. Now, for x squared, that's simple. I only have one choice, x times x. Whatever I put in the last positions has to multiply to the last number. So what I do is I pairwise factor that last number. Start with 1 in itself, because 1 will always divide into any number, then increment to 2, and ask myself, does 2 divide into 12? Yes, 6 times. Then move up to 3. Does 3 divide into 12? Yes, 4 times. The next number I would go to is 4, but since I've already written it down, I know I can stop. You always stop. You always know you have the complete list when you go full circle. What I do next is take a look at the last symbol here, which is a minus. That's going to think of subtract. So my thought process, my logic is I'm asking myself this question. What pair subtracts to the middle number of, and the middle number in this case, you don't see it, so it's always a 1. And I hope it's not, it doesn't take a lot of thinking to know that 3 and 4 subtracts to a 1. So put a 3 and a 4 here. Now I got to figure out if it's pluses and minuses. How do I do that? So I write down the numbers here and set it equal to the middle number. In this case, it's a 1, but it has a negative there, so it's a negative 1. And then this is just a puzzle. Your job is to figure out the pluses or the minuses, any combination that makes this a true statement. So play with it for a little bit, guess and check, but I hope you eventually get to a positive 3 and a negative 4 will give you a negative 1. and those are your symbols. That is the factored form of that quadratic. Number 7, same thing, factor, but the leading coefficient is not 1, so it augments your thinking a little bit. Again, the first positions has to multiply to the first term. Since it's the 3x squared, I mean, 3 is pretty simple. There's only one breakdown of 3, 1 and 3. So it has to be x, or let's do 3x. Doesn't really matter which one comes first. 3x and x. The last number is a 20, so I'm going to break down the 20 here. 1 and 20, 2 and 10. 3 doesn't work. 4 and 5 works, and then I'm back to 5. The last symbol is a minus. I'm going to think of subtraction, but we have to be we have to change our thought process a little bit. Do notice that this guy is a 3 here, and if we were to FOIL him out, whatever number I put into here will be multiplied by 3. So I have to ask myself, what pair such that, ST is such that, what pair such that when I multiply one number by 3 and the last symbol made me think of subtract gives me the middle number of 4. So it requires some mental math. I don't know what the right answer is off the top of my head, so I'm going to check. Let's check the first pair. Let's multiply the 1 by 3. 1 times 3 is 3, and then if I do 20 minus 3, that gives me 17. Not what I want. Let's multiply the 20 by 3. 20 times 3 is 60. Well, that's way too big already, so I'm just going to skip him. Can't be this guy. Let's try the second pair. So let's multiply one of them by 3. So let's multiply the 2 by 3. 2 times 3 is 6, and then 10 minus 6 is 4. That's exactly what we're looking for. So hey, I got lucky. I got it on the second guess. I've done problems where the correct answer was 3, 4, 5, 6 guesses in, but hey, sometimes you get lucky. Notice it was the 2 that had to be multiplied by 3, so I know for the fact that the 2 has to go here, and the 10 has to go here. Now all I got to do is figure out the pluses and minuses. So I'm working with a 10, I'm working with a 3 times 2, which is a 6, and it needs to equal the middle, which is a negative 4. I hope you can play around with the plus and minuses long enough to know that it should be a negative 10 and a positive 6 will give me a negative 4. So the 10 should be negative, and the 6, or the guy playing as a 6, should be positive. That is the factored form. Let me go ahead and rewrite it all cleaned up nicely. This number 7 should factorize into 3x minus 10 and x plus 2. Right? So there really is no way around it. You just have to get better at it by doing a lot of thinking, a lot of practicing. Number 8 is more of the same thing, but the only difference is the leading coefficient is a 4. So you actually have multiple choices. It could be 1 and 4 or 2 and 2. Which one is it? Is it going to be 1n and 4n, or is it going to be 2n and 2n? We simply don't know. You just have to go through them all. It's just more guess and checking. Like I said, this isn't glamorous. There is no formula algorithm. You just have to guess and check and work your way through. Does 4 work? No. 5 would work. 1 and let's see, that's 2. 4, 6 doesn't work, 7 and 10. You just have to guess and check until you get it right. So I'm not going to go through the rundown for this. I'm assuming by now you get the idea, but guess and check, you'll find out that this won't work, and the actual factored form is n plus 10 and 4n minus 7. Again, I'm skipping all the guess and check. It's the same idea, excuse me. Number 9 is more factoring, but it doesn't look like your stereotypical quadratic. Notice it's an x to the 4th. However, you should notice quadratic form. This exponent is exactly twice as much as the middle exponent, and it ends in a regular number. That is classic quadratic form. To make it look like a quadratic that we're more familiar with, you're going to let the letter u, or whatever letter you like, equaling the middle variable part, x squared. What this does is it transforms the whole problem into u squared minus 5u minus 14. And hopefully that looks more like a traditional quadratic that we can factorize. So that factorizes into u and u, minus 7 plus 2. Okay. That would be the factored form for the u quadratic, but our original problem started with x's. So wherever you see a u, just back substitute the variable substitution. So the factored form should be x squared minus 7, x squared plus 2. Okay. Number 10, I'm asking you to factorize a cubic, but the important thing is it has 4 terms. If I ask you to factorize something that has 4 terms, more likely than not, the technique will be factor by grouping. What you do is you sort of break down the problem into 2 pieces. First 2 terms and the last 2 terms. And notice how I included the symbol or the sign with the second highlight. So when I rewrite this, I'm going to put the 8x cubed minus 7x squared in its own parentheses, always a plus sign in between, and then include the middle symbol here. So this plus sign will always be there. You'll always use pluses, and then this plus came from that guy. So just keep that in mind. Then all I got to do is GCF, greatest common factor. So from the first group, I can pull out an x squared, leaving behind an 8x minus 7. From the second group, I believe I can pull out a 5, leaving behind an 8x minus 7. And notice that the parentheses here are the same. That's what we want. Because the parentheses are the same, we can factor him out. But with all factoring, you always put the leftovers in their own parentheses. And the leftovers, I hope we can see, are the x squares and the plus 5. That is the factored form of the original problem. In number 11, it's a multiplying rational expressions. And as I said during the lesson, it's sort of ironic. When it comes to multiplying and dividing rational expressions, you don't do any multiplying and dividing. All it is, when it comes to rational expressions, anything, is factor and cancel. So the first thing I'm going to do is just factorize everything. I'm going to factorize this guy. I'm going to factorize that guy. I'm going to factorize that guy. Factorize that guy. So this would equal, since they're all binomials, it's no special techniques, it's just GCF. So for the yellow, we can pull out a 2k, leave behind a k plus 2. For the light bluish, we can pull out a 2k, giving us a k plus 4. For the orangish reddish, we can factor a 3, giving us a k plus 1. And for the pink looking highlights, we can factor out a 12k, k squared, leaving behind a k plus 1. And then just start canceling like crazy. We can cancel out the k plus 1s. I can cancel out the 2k's. Now the 3 and the 12, although I can't cancel them out completely, I can reduce them. So I can divide out a 3. So this 3 is gone, and this 12 becomes a 4. I believe that's all we can cancel. So you're going to, quote, multiply straight across. Now, some teachers make you actually FOIL it out. I said in class, if you want to leave in factored form, go ahead, I'll accept it. So the only thing that's left over on top that's not crossed out is the k plus 2. And the only thing that's not crossed out in the bottom is this 4k squared with the k plus 4. I always like to put the monomials in front. So 4k squared and the k plus 4. And again, you don't have to multiply them all out. That is the product. Number 12 is a same idea, literally the same idea once you put it in the right formats. Notice we're dividing by a fraction. And I hope we've all learned in elementary school, to divide by a fraction, you change it to a multiplication, and then you do the reciprocal of the divisor. So this equals, keep the dividend, the guy you're dividing into, the same. Change the division to multiplication, and then take the reciprocal of the divisor. Then it becomes like the problem, like number 11. So again, just factor everything and cancel. I'm going to factor this guy, I'm going to factor this guy, I'm going to factor this guy. So the yellow you can factor out of 3, x minus 4. The blue you can factor out 8x squared, gives us x plus, oh no, 4x squared, sorry. You can factor out 4x squared, gives us a 2x plus 1. And then the orangish red, you can factor out 4x squared as well, giving us 2x plus 1. Hey, they were the same. I guess we could have canceled out at the beginning. So sort of a trivial situation. 4x squares, 2x plus 1 cancels. Well, that was easy. And all you're left with is a 3, x minus 4. Right. I guess we could have, I didn't notice it because I was on autopilot, we could have canceled these guys out from the get-go because they are literally 100% the same. Number 13, simplifying complex fraction. Lots of techniques to do this. The technique I showed in class and the technique I like is clearing the fraction. But to clear the fraction, we need the LCD of all the inside denominators. What do I mean by inside denominators? I mean these little denominators here. If you forgot how to find the LCD, the one thing I like to do is line up all my denominators vertically, that means on top of each other, and factor them. There's nothing I can factor from x minus 1, so it stays as x minus 1. But do notice I put them in parentheses because the x and the minus 1 belong as one thing. I can't break down the 3 any further, and same thing with the x minus 1s. So the LCD equals, you start by looking up and down, not left to right, but look up and down and see if you have any common factors. Hope it's very easy to see that we have the x minus 1s in common. X minus 1s. After you do all the common factors, any loose factors that you did not circle belongs in your LCD. There we go. There's our LCD. Next, what I'm going to do, just to give myself some space, I'm going to rewrite the problem, 6 over x minus 1. I'm going to deliberately give myself some space, then minus x plus 2 over 3, all over 3 over x minus 1, space, minus x plus 2 over x minus 1. That gives me room to multiply everything by the LCD. 3x minus 1, 3x minus 1, 3x minus 1, 3x minus 1. If we played our cards correctly, since we're using the LCD, all the denominators should cancel out. X minus 1s cancel, 3's cancel, x minus 1s cancel, x minus 1 cancels, and then all you got to do is just multiply the rest. Be very, very careful. When it comes to subtraction, as we do here, you actually have to distribute that negative as well. A common mistake students make is they forget to distribute that negative. So in the top left, all I have is 6 times 3 is 18. In the top right, I guess I'll just show my work. It's a negative x plus 2 times x minus 1 over, bottom left is 3 times 3 is 9, minus, and in the bottom right is a 3x plus 2. And then just go ahead and distribute, being mindful of the negatives. So that's 18 minus x squares minus x plus 2. All I did was I FOILed this guy out and distribute the negative. All over 9 minus 3x minus 6. And then you just go ahead and combine like terms, and we're done, I think. So we have... what's that? Negative x squares minus x. So the only like terms we have are the 18 and the 2, which gives us a 20. And then the denominator, the only like terms that we have are the 9 and the negative 6. So we have a negative 3x and then a plus 3. I guess technically you could factor this and see if anything cancels, but nothing cancels out. So that is our simplified form. Number 14 was just a simple solving a linear equation. Lots of different ways to solve again, lots of different ways to do all these problems, but I'm just going to showcase one possible solution method. First thing I notice is I have a lot of parentheses, and let's break them down by distribution just to make things easier for you. So just go ahead and distribute. Be mindful of the first distribution. It's a minus 7, so you got to distribute that negative as well. So that gives us 7. Distribute the negative 7. Gives you minus 7x minus 56 equal, distribute this 7, gives us 7x plus 35. Let's combine like terms first. So I got a 7 and a minus 56. So that gives me negative 7x minus 49 equals 7x plus 35. And it just becomes algebra 101. Get all the variables on one side, get all the regular numbers on the other. So hopefully we can do this 2 steps at once. I'm going to add this 7x over, just to keep the x's positive. And at the same time, let's subtract the 35 to move the regular numbers to the left. This gives me negative 7084 equals 14x. These guys are gone. And divide both sides by 14. And hopefully that goes in evenly. Negative 84 divided by 14 gives me a negative 6. So just straightforward solving linear equations, simplify both sides, and then solve. Number 15 is an absolute value linear equation. Now, how that changes your thought process is before you can do any solving for the variable, you want to get the absolute value stuff by itself. So I hope by highlighting it's very clear that my first step is to get rid of that plus 8. So very simple. Let's minus 8 from both sides. I guess I'll show it for the notes here. Minus 8 gives us absolute value of 10k plus 10 equals 70. Now the way we approach absolute value is to simply use its definition. Recall that absolute value of stuff, anything, absolute value of x will always give you one of two things. Itself right back out, or the opposite of itself. Now it'll give you itself if what you put into it is not negative, and it'll give you the exact opposite out if the thing you put into it is negative. However, since what we are putting into the absolute value in the equation has a variable in it, we don't know if he's always positive or always negative. So as a mathematician, we have to hedge our bets. We have to consider both situations. So we apply the definition using both possibilities here. So according to the definition, the absolute value of 10k plus 10 could give me the identical thing right back out, which, according to the problem, equals 70. But we do know it's possible to get the exact opposite out, and to do opposite, you just wrap everything in parentheses with the negative in front. And that also equals 70. So then to solve this equation, you just, solve both of them. Let's work the left side first. I'm going to subtract the 10. 10k equals 60, and then divide out the 10, k equals 6. On the right side, you can go ahead and distribute the negative if you want, but I personally like to divide out a negative 1, just so that my solving steps will be the same afterwards. Negative 70, and then just go ahead and subtract the 10, as we did before. 10k equals negative 80, and then divide out the 10, k equals negative 8. Now, technically, good problem solvers always check their answers, but if we take a look at the equation before we apply the definition, this line here, notice how it equals a positive number. There's no extra variables involved. If you trust your math step, any absolute value equation that just equals a simple number, whatever answer you get is whatever answer you get. So I'm pretty confident in our math here, so I'm not going to bother checking. Those two are our answers. Number 16 was a quadratic equation, and I believe the instructions, I try to give you a hint. I said solve by factoring, but honestly, in my class, I don't care what method you use. Factor, quadratic formula, complete the square, I don't care, as long as you get the right answer. Well, the idea to solve a quadratic is you want it to equal 0 on one side. So we want to move everything onto one side. So let's move everything to the left. So I'm going to add 6a squared to both sides, and let's see if we can do 2 steps at once. Let's subtract 8a at the same time. That's going to give us 7a squared plus 29a minus 30 equals 0. And then just factor it. Or quadratic formula or complete the square, your choice. 7a, 30, 1 and 30, 2 and 15, 3 and 10. And I'm thinking subtraction. So times 7 and subtract. Let's see. What would this be? Oh, I forgot. No wonder it's not working. I missed a 5 and the 6. Yeah, I was guessing and checking these three, and none of them were working. But 7A and A. 7 times 35. Yes. So this one here, 7 times 35, and then minusing the 6 should give me the 29. So it's 7 and 5. 6 is by itself. 6 is negative. 5 is positive. So the idea is that once you have it in factored form, the zero product property set each individual these factors, because it equals 0, that's an important thing, you just set them equal to 0 separately and then solve. So the left equation, you add the 6, divide up the 7, A is 6/7. On the right equation, subtract the 5. A is negative 5. Those are your two answers. Number 7 is a rational equation. Looks scary complicated, and there are, again, with everything, lots of different techniques to solve. I like clearing the fraction. So if the LCD is not obvious enough, let's just run through the motions. First thing I'm going to do is write down all the denominators in stacked forms, factor them if I can, which I cannot. So the LCD, you start with the common factors, which you have 1, and then write down all the leftover factors, which I have none. So x minus 5 is my LCD. I'm going to go ahead and rewrite the problem with some space. And then go ahead and multiply everything by the LCD. All the denominators should cancel out. So we're left with x plus 6 plus x squared minus 6x plus 8 equals, and just go ahead and FOIL this guy out, giving you x squared minus 8x plus 15. Then you just go ahead and combine like terms, solve, and go home and be happy. So on the left here, we have these x's as like terms. We have the constants as like terms. So we have x squared minus 5x's plus 14 equals x squared minus 8x plus 15. I hope everyone can see that when I subtract the x squares, they're gone. So this is just a regular linear equation. So let's get all the x's on one side and the numbers on the other, which means I'm going to add the 8x over and subtract the 14 over. 3 steps at once. Doing pre-calculus now. So we have 3 x's here equals, what's that, 1? So x equals 1/3. When it comes to rational equations, it's not an option. You must check your answers, but you only need to check your answers against the denominators. Now in this problem, we only had one unique denominator, x minus 5. What you want to do is prevent dividing by 0. So if I were to plug my possible answer into the denominator, the question I'm asking is, does it equal 0? If it does, I have to throw away my answer. In this case, 1/3 minus 5 is not 0, so that means this is a good answer to keep. Last but not least, radical equations. Just like with absolute value, you want to get that special symbol, radicals, absolute values, parentheses, what have you, by itself. Now here's my radical expression. Notice how it's already by himself, so we just can go ahead and get rid of the square root, knowing that the opposite of a square root is a square. So that's our first step, to square both sides. Now a common mistake I saw people make is they want to distribute that 2 and say, oh, it's n squared plus 1. That is a false statement. You can't apply the power property because it's a binomial, that plus sign, that screws things up. So the proper way to square a binomial is you either use the pattern or know that squaring is multiplied by itself, and then you just go ahead and FOIL it out like normal. And that's going to be n squared plus 2n plus 1. So this right here should go on the left-hand side. So we get n squared plus 2n plus 1 equals, and then on the right-hand side, when you square a square root, that just goes away. And then it becomes a regular quadratic to solve. Move everything to the left, I'm going to minus the 2n, minus the 2n, minus the 50, minus the 50. You get n squared. These guys are gone. Minus 49 equals 0. So this is actually a special situation. It's no longer a trinomial, and there's only one variable term. So we can actually just solve this directly using inverse operations, or since n squared and 49 are both perfect squares, we can factorize it using difference of two perfect squares. Doesn't really matter. I've been factoring all day. Let's just go ahead and solve it using regular algebra. I'm going to add 49 on both sides. N squared equals 49, and then the opposite of a square is a square root. Do note, however, that the blue, is our action, so we are using a square root to solve. So whenever you use a square root to solve, your result will be plus or minus. Now, just like with absolute value equations, we have to check our answers if our original equation had variables on both sides, which, if you look at the original equation, before we squared it, it had variables on both sides. So we need to check. So let's check n rather. N equals 7, and we plug it into the original equation before you squared things. So plugging in a 7, that's an 8. So 2 times 7 is 14, plus 50 is 64, and indeed that is good. So n equals 7 is an answer. Let's check negative 7. That's negative 7 plus 1 equals square roots. 2 times negative 7 plus 50. That's negative 6. 2 times negative 7 is negative 14 plus 50 is 36. Negative 6 equals 6. That's a false statement. So I have to throw away the negative 7. That's bad. There's only one answer, a positive 7.